Sir.
Good evening. Good evening. So
Good
I
evening, sir.
I will suggest that you can mute yourself such that we can continue our class very nicely. So in the last three classes, what we have done, we have learned all about the Dirac notation and the concept of Hilbert space. So obviously we are in the process to building the tools of quantum mechanics, and we will go for the next tool, and this is the very interesting one, that is operators. They are basically linear operators and matrices. So in quantum mechanics, the operators and matrices both are same thing, and how we can uh, use these operators to understand the quantum mechanical phenomena, that is the part of postulates. But right now we have to just understand what are basically operators and how we can use it and what should be its property. Today we will also discuss the eigenvalue and eigenvectors. I will just discuss the concept only. The main thing, the practice part, you will be discussed into this particular mathematical physics course. So let's try to understand what are operators. So these are mathematical operators. So they are some mathematical operations, and what are meaning of that? Let's try to understand. So in general, in quantum mechanics, we will try to write the operator with capital Roman letter with some hat. So this is A hat. You can write some B hat. So in quantum mechanics, whatever be the measurement you have to do, there is associated some operator. Suppose you want to measure a position, there is associated operator. Suppose you want to momentum, there is associated operator. Suppose you want to project one vector to the another vector, there is associated operator. And every operator is unique, and it has unique purpose to solve to use all this mathematics into quantum mechanics. So what is meaning of operator? In general, we will take A hat, B hat. It is very good that we have to take the hat on this particular capital Roman letter, but during the process, we become so lenient that I can use that only A as operator, B as operator. So we will define operator A and operator B. This kind of situation is there. So what is operator actually? When you are talking about operator, it have to be operate on some function, and that function can be represented in term of kit, and that function can be represented in term of some in general function, continuous function. So what are operator? In a very simple way, if A is a operator, it will operate on any kit. So how you will operate? So this is the kit. So this particular kit, suppose you have kit, then you will operate A from the left hand side. So you will operate A on kit. You can get some another kit, and this kind of situation can be there. Suppose you have another operator B and it is operate on phi, you may get another kit. So kit will be transformed to kit. So kit will be going to transform to kit, and this is all about the meaning of operators. And these operators can be represented in a functional form. It can be represented in a function of x. It can be represented in a function of momentum. So it will depends which kind of situation we are going to face. We can define that kind of operator. But in general, if we representing our function as a kit, then this operator is nothing but matrix. And obviously in quantum mechanics in general, we will take n cross n matrix. So this will just tell you about this operator. But obviously, if I can represent this function as a some continuous function, then this operator will also have some functional form. For example, you can define operator which will differentiate any function. So it may be named as differential operator. So let's say I define my function dx, and which will be define, this is the notation. And what will be actual thing? I can define mathematically d upon dx. So this is differential operator. So what we will do, we will just try to operate differential operator on some function. Let's say we are operating it on some function phi x. What is meaning of that? This differential operator will operate on phi x. You will get some new function. And what will be new function? This new function is nothing d upon dx phi x. And obviously whatever be this value, you can get it. It may be same value, it may be different value, depends on what is operator, depends on what is the function. For example, in a very trivial example, you can take that suppose operator dx is defined as d upon dx, and we are just going to operate on e to the power alpha x. Then what will happen? We will get d upon dx e to the power alpha x. I can get alpha e to the power alpha x. So it is same function here with some number. It may be different function. So if you can take this particular situation, suppose we have dx and it is going to operate something sine alpha x, then you will get alpha, and this will be written as d upon dx sine alpha x is equal to alpha cos alpha x. So you can have entirely different function. So sometime operators will have exactly same function. It may be proportional to that function. It may be different function. So, and yes, you can represent any operator in a matrix form. So operator can be represented in a matrix form, but you have to define in a basis, that in which basis you just want to represent your operators. So we will talk it later, but before that, what are the linear operator? Why we are saying it is a linear operator? We will just try to understand. So this kind of situation is there. So operators can be represented in a matrix form. So today we will learn how you can write operator can be represented in matrix form in some basis. So you have to define what are the basis. Unless until you will not define basis, you cannot write matrix actually. So this is the very interesting kind of thing. If you have any doubt, this is just a initial definition. We will just try to do how we can use it. So if you have any doubt, you can just ask me. Okay, so let's go for why we are saying it as a linear operator. So we will just have, it will follow some rules and regulation, and you can just use it as a linear operator. So, so what we have, suppose we have any operator A, and it will operate on some ket. I am writing in form of ket, that is because it is more educated, more you can use it frequently for quantum mechanics in a ket form actually. So this can be written as, so this is equivalent to a phi plus a psi. So this is all about operators. So why it is linear? Because it is operating it linearly. And now you can just write a plus b, and if you will operate on phi, then obviously that will be a phi plus b phi. So you are using it linearly. But the most interesting thing is that in general, AB is equal to not BA. In general, AB is equal to not BA. Means if you are operating A first and then you are operating on something, it is not necessarily that it will equal to if you are operating B first and you are and after then you can operate A. So in general, operators are non-commutative, but sometimes it may commutative, and that is known as commutator. So we can have, so in general, so this is not a strong statement. So you can use in general. In general, AB is equal to not BA. By the way, if I am operating A, B, C on, let's say, some ket phi, what is the meaning of that? Meaning of that, this C will operate first. So this is my first operation. And after operation, it will give you some new thing. Then B will operate on this new thing. So this will be second. And after then, you will operate that third on B, C, phi. So this will be my third operation. So which one is the closest to this particular C? Sorry, which one is the closest to particular ket operator, that will operate first. Now, if you are writing something like that, phi and operator A, this is meaningless. This has not any meaning. This is meaningless. This is void. Similarly, you can operate for bra also. So you can operate phi, and let's say you can operate D operator, you will get the bra. So obviously, if you will operate the ket, you will get always ket. You will operate the bra, you will get always bra. It is not possible that you will operate on ket and you will get the bra. Sorry, it is not possible. So similarly, if you are writing, suppose this phi, and you are writing D something like that, this is void. Void means it cannot be possible. So this kind of situation is always there. Now, the most interesting question is that, suppose I have A, and A will operate on any ket phi. Suppose A will operate on any ket phi, you will get psi. So we are talking about correspondence between bra and ket. So means if I know the relationship of ket, I also know the relationship of bra. So this is the wonderful thing. So what I have, suppose it is given. So it is given that A will operate on phi, you will get psi. My question is that, what will operate on phi bra such that you will get the psi bra? This is the most interesting thing. Suppose I will operate A on phi, I will get psi. My question is that, what will operate on phi such that you will get psi? Then if ket is transforming to bra, if ket is transforming to bra, then operator A will transform to A dagger. What you will say? It will say dagger. A cross, you can say A cross, something like this. A dagger. What is A dagger? A dagger is nothing. You will take the complex conjugate of each element and you can transpose it. So this is identified as A dagger. So what will happen? If ket will, if you have information of ket, you can have information of bra also. So this is very trivial, because ket means what? Ket means you will just column vector, and corresponding bra means what will happen? You will have row vector, and every element will go to conjugate, complex conjugate. So similarly, we are doing same thing. We are just going for the complex conjugate, and after then we are transposing. What is meaning of that? Meaning of that, ket is transforming to bra, and bra is, sorry, column vector is transforming to row vector, and row vector is transforming to column vector. So this is the way we can have correspondence between bra and ket. Similarly, you can write something like, similarly you can write, suppose you have information of bra. Suppose you have information of bra, let's say phi bra is there, and you will operate bra on, sorry, this B operator on bra phi, and let's say you will get some chi. You can get some new chi. Now my question is that, what will operate on phi ket such that I will get chi ket? What we have to do? We have to again go for this B dagger. And what is B dagger? B dagger is nothing but B star, and we are taking the transpose. So this is very interesting thing. So let's try to understand the what is properties of this particular dagger. Up to this, if you have any doubt, you can just ask me. These all are very simple, very trivial. You have to just understand the rules and regulations. But when you will go for the application part, then it is very interesting. Okay? Okay.
हेलो सर. हेलो सर.
Yes.
सर ऊपर
Yes.
ऊपर राइट साइड में ऊपर थोड़ा क्लियर नहीं हो रहा है.
Yeah.
राइट.
This one.
हाँ सर.
This one. This one.
नहीं सर, इधर राइट साइड में जो अभी आप बता रहे थे.
Yeah. This one.
हाँ.
Okay. Listen. What will happen?
ऊपर राइट.
मेरा क्वेश्चन ये है, this one or this one?
नहीं सर, एकदम ऊपर 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 उसी साइड में.
This one. This one.
जी जी.
Okay. मैं ये कह रहा हूं कि ये अगर आप लिख रहे हो तो इसका तो कुछ मीनिंग है, लेकिन गलती से अगर आपने ये लिख दिया और यहां पर ऑपरेटर लगा दिया तो इसका कोई भी मीनिंग नहीं है. ओके? This is meaningless. This is meaningless actually. Okay? Listen, what is actually meaning of this thing? This is very interesting. Actually, this thing is something like 1 and this thing is going to close. This is meaning of that. So you have to operate from here only. Okay, you can operate from here only. But in general, we are not using this 1. We are just putting this bar there. Okay, so this is the notation. So this bar is for to fitting the operator on this particular kit. And this means you cannot apply anything, any operator from this side. So this is all very abstract notation from the Dirac. And it works. It works. You will find when we will apply this thing, it works. So I think it's okay. So let's try to go to understand different properties of a dagger. And one property is really very interesting, and I will also derive it. So let's try to get this all properties.
Sir.
Yes.
Sir, the A dagger operator is only applicable for matrix type of thing, or it's applicable for other thing also?
No. It is applicable for everywhere. Everywhere you have to find this operator complex conjugate variable, Hermitian conjugate. You have to find for that operator also. Okay, we will discuss. When times come, we will discuss what we will do. Okay.
Yes.
So whatever we are doing at kit, it will also do to this particular functional form. So there is not anything that we are just going for the kit only. You have to go for functional form. Okay. Anyway, but right now we are just going for the definitions. So and properties. Okay, application part will be next time. So what we have suppose a dagger, and we will take the dagger. What you will take? You will take a. Suppose some function is lambda and it is a scalar number, and you will just take the dagger of all this thing. You will get lambda star a dagger. Next you can have, suppose you have a plus b, and you can write whole dagger. Then you can write a dagger plus b dagger. And obviously in an operator you can write a plus b is equal to b plus a. For operator you can write a plus b is equal to b plus a, and if you are taking the dagger of whole, you can write something whole dagger. So there is not any problem. So you can use this thing. But most important thing is that if we are writing a b dagger, what will happen? This will be b dagger a dagger. So if we are writing a b dagger, that means it is equal to b dagger a dagger. Let's try to prove it. It's a very interesting proof to understand the nature of operator. Yes, lambda is a scalar quantity, some number you can have. Okay, then you have to do this complex conjugate of that number also. It is very trivial. Why? Because if you take the lambda inside the matrix and again you will take the complex conjugate, the same thing going to happen. But yes, it is given into book, so I have used it. Let's try to derive it. It's a very interesting. The derivation will very interesting to understand the how to operator operates into kit and bra. So what we have uh, we have very interestingly, let's say A, B will operate on some kit. Let's say it will operate on some kit. What I will get? I will get psi. And yes, if A is operator, B is operator, AB is also operator. So if you have any confusion, don't worry. If A is matrix, B is matrix, AB will multiply, it will give you matrix. So this is very simple. Now, if I am writing this statement, can I write the same statement for the bra from my correspondence principle? We can write it for the bra, and that will be, we can write phi AB whole dagger is equal to psi kit. Means if this holds correct, this must be there. This must be there. Means if you know the operation of kit, you can write the operation of bra. You can assume this is a sum operator, AB is sum operator. When we are writing for the bra, what you will do? You will just take the dagger. But now look at how you will explore all this thing. So how it is going to operate? So first B is going to operate on phi and it will give you some buffer. What will operate? B will operate on phi, it will give you some buffer. Buffer means you don't know what it is. And then A will operate on that particular thing. So this is the rule because we have understand the rule. So what I can write, and this is for the buffer. So B is operating for phi, I can get, let's say chi. If B is operating on phi, let's say I can get chi. What is meaning of that? Meaning of that, I can write phi B dagger is equal to chi. Means if this holds, it must be there. If this holds, it must be there. Now let's try to go for it for the next one. Next one, A is operating on B phi, which means A is operating on phi. Means I can write the whole story something like A is operating on B phi means A is operating on chi. What I will get? I will get psi because I have assumed from initial condition. We have just write it from initial condition AB phi is equal to psi. So AB phi must be equal to psi, and this is the buffer. This is the buffer. So if you will look this particular buffer, how you can write it in this side? If this holds, I can write psi, sorry, I can write chi bra A dagger must be equal to psi. And now from here, and now the purpose of this one is over. Now let's come to this. Can I write this psi as B dagger phi? I can write this psi as B dagger phi. Sorry, this chi as B dagger phi. So I can write something phi B dagger A dagger is equal to chi. So now you can compare this equation, equation A and equation B. The right hand side you have same thing and the left hand side this kit is same, then this is equivalent to this. So we can prove AB dagger is equal to B dagger A dagger. Are you getting it? So this is a wonderful proof. I will suggest you that you can go home and do this proof again to to understand the how the kit and bra will be correlated to each other. And this is a wonderful proof. We can have different type of proof in the mathematics, but I have used actual proof from the quantum mechanics. So if you have any doubt, you can just me. Okay, so this is all about correspondence of kit and bra. So it is very interesting. It is very interesting. If you are writing for the kit, then for bra, sorry, if you're writing this thing for a kit, for bra, you have to write
Sir,
this thing. Yes.
सर ये काई एयर डैगर जो है वो ब्रा साई कैसे आया?
This one?
ये नो सर below one step below.
This one?
Yes sir.
Okay. Look at here. Look at here first. Now A have to operate on B phi, sorry,
Yes,
B
sir.
phi. Okay. And B phi is nothing but chi.
Yes sir.
So A will operate on chi. What it will give? It will give psi, isn't it? Yes or no?
Yes sir.
Yes. And then you can write it in the same fashion.
Okay sir.
It's okay?
So this bra also converting this cat.
Are you getting this?
The psi cat of psi will also transform in bra of psi. When
Yes, this will be transforming to there for the bra. Same as here. Okay? Are you getting it or not? You have to respond if you are asking the question.
Yes sir.
Okay. Okay. So, and now this is the whole structure of this operator. So we have different types of operators. So you can have n number of operators in quantum mechanics. You can make new type of operators in quantum mechanics. You can, as the time progress, we will have a number of operators, and all operators have different type of its particular meaning, its particular uses. So I am not going to write it each and every operator, but some operators are very interesting. For example, in quantum mechanics, you will have momentum operator, px. It is nothing but minus I h cat del upon del x. This is momentum operator. You have operator parity operator. What is parity operator? Parity operator is pi. What is meaning of that? Meaning of that, it will operate on any function x. I just want to do x to minus x. What I will do, use the parity operator. I will get psi minus x. So this is parity operator. N number of operators you can have. Hamiltonian operator. Hamiltonian operator is all about to measure measure the energy. So you can have Hamiltonian operator. You can write Hamiltonian operator H, and this will be nothing but px square operator by 2m plus potential energy Vx operator Vx. Suppose you can write this px, and now px and Vx are operators. So we will discuss when we will apply it. We will try to discuss. But right now, I just want to discuss one very important operator that is known as projection operator. And why we have projection operator and what is completeness relation, we will try to discuss. And this is the most important thing about the quantum mechanics. This is the most important thing. In general, if you will write something like, let's say, phi and chi. This is phi and this is chi. First you will write kit and bra. So this is kit and bra. You will just match the tail. If I am writing something like this is nothing but operator. These are operators. So this is the one of the representation of operator in form of kit and bra. And the famous operator is known as that is represented into this way is the projection operator. So let's try to understand what are projection operator. I will just give you lot of hint about this thing, what it will do, and why the projection operator is so important for any quantum mechanic, to understand any quantum mechanical phenomena. Suppose I am taking a simple notation. Suppose I have one vector chi. This is one vector chi, and there is another vector into same basis. I have phi. So I deliberately represent vector like that because it has some feeling to us about the vector. Okay, but you can hope it may be function, it may be anything. So this is the chi and this is phi. What I want project psi in a direction of phi. What I want project psi in a direction of phi. So I am just writing project psi in direction of phi. So we have to project psi in direction of phi, means we have to write what will be the parallel component of psi in direction of phi. So what you will do, you will make a projector operator, and let's say I am just giving the notation pi phi. So we have to make a projector operator for the phi, and this is defined as phi phi. This is defined as phi phi. So these are the projector operator. Now I have to operate projector operator p phi on the psi. We have to operate projector operator on psi. What is meaning of that? Meaning of that, p phi can be written as phi phi, and we have to operate this thing on psi. So this will be psi. So you cannot give the 2 bar, that will be always 1 bar. Suppose I am writing phi and then I have to multiply with something, then this will be the thing. So don't give the 2 bar, that is only 1 bar. Now look at what is this thing. This thing is nothing but a scalar product. And what is a scalar product? This is nothing but number. This is nothing but number. So you can write this thing as sum alpha and phi. I can put this value as alpha. So what you have done, you have just project psi operator in direction of phi. And to realize much more, if you will operate any operator on a phi, if you project any vector on itself, you will get the same vector. So what you will get? You will get phi phi. If I operate it on a phi, then obviously phi and phi will take 1. So this will be 1. So this will be phi. So here I have to make sure that phi must be normalized. So when you are talking about projector operator, phi must be normalized. And then you can write something like this. So what will happen? Phi will operate on phi. You will get the same vector because this value is 1 because it is normalized. So this is the projector operator, and we will use this thing n number of times to understand the quantum mechanical phenomena. These all are very abstract. Don't worry, these all are very abstract. The physically understanding all this thing is very tough, but yes, it works. And now if you have any doubt, you can just ask me. Okay, so let's try to go for a next particular thing, that is completeness relation. And this is one of the most interesting thing in a quantum mechanics. And why we are taking this completeness relation, this is very important. Now, Suppose I have n number of vector, let's say phi 1, phi 2, phi n. So I have n number of vectors, and what I get, if I get summation over n phi n, phi n is equal to identity x, then this relationship is identified as completeness relationship. So this relationship is known as completeness relationship. In a very simple way, I can dare to say this, that it will complete the information of a vector. It will give you complete. It is very in a very layman language. I just try to talk it, not in a scientific language. But yes, we are human beings, so we need to talk in a very layman language. And when we are talking about in a very layman language, I can say it will. If you know this thing, means you know the complete information of a vector. We will talk it later, but right now we will explore it more and more into this postulates. But right now I will just give you one example. Suppose I have phi 1 vector, this is 1 0, and second I have phi 2 vector, that is 0 1. We have to check that they will satisfy this completeness relation or not. So what I have to write? I have to write phi 1 plus phi 2 phi 2. And what is phi 1? 1 0. What is phi 1 bra is 1 0. Plus what is phi 2 is 0 1. What is phi 2 is 0 1. And now this is not a number, this is a matrix. Row into column is number, column into row is matrix. Now what will be this matrix? 1 into 1, 1, 1 into 0, 0, 0 into 1, 0, 0 into 0, 0. Plus, you can write this thing as 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. If you will add it, if you are going to add it, then you will find this thing as 1, 0, 0, 1. So yes, this will fulfill the completeness relation. This is going to fulfill the completeness relation. This is very trivial, but I will give you the one more non-trivial example. So let's try to go for the non-trivial example. So
Sir,
up to this, are you comfortable?
sir,
Yes.
sir, this capital N, should it be equal to the dimension
Oh,
of
sorry.
the Hilbert space?
That capital N should be dimension of Hilbert space. How do you, what is meaning by him dimension of Hilbert space?
And
First,
sir, how many phi should
you
we get?
have
I
you
mean,
have dimension of any vector. You have dimension of any vector. You have infinite number of this capital N, isn't it? You have not necessary that you have some finite number of capital N. You have dimension of any vector, isn't it?
yes, sir, I'm not able to understand that how many phi should we take? I mean, we can take only 3 phi or
Of
4
if
how
you
many?
want to make the space of 3 cross 3, then you have to take the 3 phi. If you want to space in a plane, then you have to, the 2 phi is only more than enough. Look at in this different way. Okay, I can understand what is your problem. Suppose you want to fulfill all this place. How many phi you needed? Only 2 phi.
Yes, sir.
Yes. If you want to fulfill all this space, something like 3 dimension, how many phi you need? How many unit vector you need?
3.
3. So it will
Yes.
depends. Okay.
Oh, okay, sir.
Okay. Now let's try to go for next example, and that is more non-trivial example. So, okay, so let's try to go for, let's say the phi 1 is all about 1 by root 2, 1, 1, and phi 2 is all about 1 by root 2, 1 minus 1. So what I will do, I will just go for phi 1, phi 1 plus phi 2, phi 2. Let's try to figure it out. What is this particular value? 1 by root 2, 1 by root 2. And this value is 1 by root 2, 1 by root 2 plus 1 by root 2 minus 1 by root 2. And you can write 1 by root 2 and minus 1 by root 2. So let's try to figure it out. What will be the value? So 1 by root 2 into 1 by root 2, I will get 1. 1 by root 2, 1 by root 2, 1, 1, 1. Second one, that is 1. This is, sorry, this will be half. Sorry, this is half. This is half. This is half. This is half. So this will be half, and this will be minus half. This will be half. Sorry, this will be minus half, I think. This and this is minus half, and minus minus is again plus half. You will just calculate 1, 0, 0, 1. You can find. So yes, it will also fulfill your same purpose. It will also try to fulfill your same purpose because it will also satisfy the completeness relation. I am giving you one homework that you can just go for it and try to see that these vector will satisfy or this vector will fulfill the completeness relation or not. Just I am, and obviously it have to be orthogonal vector. So I am taking 1, 0, 0, 1 by root 2, 1, 1, 0, and 1 by root 2 can take 1 minus 1, 0. So you have 3 vectors. Just check it out that it will follow this particular thing or not. But thing is that why I want this thing. This is the most important question of the quantum mechanics. Look at, now again I am going to my first class of tools of quantum mechanics. Let's try to go the analogy part. Let's try to go the analogy part. And what are the analogy part? It's a very interesting. Now, what I have written, I can write any vector as a function of C sub, let's say this is A1 I, A2 J cap, A3 K cap. So what are these? These are the basis vector. And these are the orthogonal in nature. And you can say orthonormal in nature means I dot j must be equal to 0. I dot I must be equal to 1. I dot k must be equal to 0. Similarly, you can get all this kind of thing. Now, if I will ask you, what is value A1? How can you determine the value of A1? What you will do, you will just take the dot product of I with A. What you will get? A1 I dot I plus A2 I dot j plus A3 I dot k. And what will happen? I dot I is 1 or other part is 0 because I know these are the orthonormal vectors. So what I have, I dot A is nothing but A1. Similarly, I can write J dot A is nothing but A2, and similarly we can write K dot A is nothing but A3. Now can I write this vector as I dot A, and this is actual thing we will do into the quantum mechanics. Can I write A vector as I dot A I cap plus j dot a j cap plus k dot a k cap. We can write this vector. Means if we know the vector and we know the basis, we can write vector in this form. These all are the unit vectors. So I think this is a very trivial exercise for you, that how we can write any vector. Now let's try to go for same thing for a Dirac notation or Hilbert space, the vectors which are used into the Hilbert space. Now look at what we can do. It's a very interesting. So I have keeping this thing as same. Suppose I have any vector psi, and what I have, I just want to write psi in a basis of phi 1, phi 2, phi 3. So what I have, phi 1, phi 2, phi 3 up to phi n. So what I have n number of, so I have one completeness relation, and this will be 1. So if this is going to form us, if all the phi's, phi 1, phi 2, phi 3 up to phi n is going to follow the completeness relation, we can do a beautiful exercise. What is this beautiful exercise? I can write psi is equal to identity of psi. Psi is equal to identity of psi. We can write it. Yes. And now this identity can be replaced by this information. So this can be replaced by n phi n psi. So I have put this I here. What I have, if you are taking all this particular psi, this is nothing but a number. Phi and psi is nothing but a number. You can write the whole stuff something like psi is equal to summation over n, and this is phi n psi in a bracket. I can take it in a bracket as a phi n. And please mind it, this phi n is an orthonormal vector. So what we have done, we have construct a vector in some orthonormal basis. And now this phi n can be n number of vectors. This phi n can be n number of vectors. So we can construct a vector which is n dimensional, which can we have n number of direction. Look at, you can just match these two things. If you want, I can write it something like psi is equal to phi 1 psi plus phi 1, and sorry, it will take long thing. So I can write something like, here I can write this all thing as, I can write, if you want, I can just more simplify this. I can do this more simplification, phi 1 psi phi 1 plus phi 2 psi phi 2, and so on. So what you have exactly same sort of practice here. This is exactly same sort of practice what we are doing into our in general vector into the Euclidean space. And you can construct n number of vectors. You can construct n number of vectors like that. And in the same basis, you can have a number of vectors. Whatever with the psi, if I know the psi and I know the phi n, I can construct the vector. Yes, it is suppose it is 3 vector, then it is 3 dimensional, it is 4 vector, then it is 4 dimensional vector. So you can construct the vectors due to this completeness relation. And it is so important into the quantum mechanics that which kind of vector are needed into the quantum mechanics is all about which vectors will follow something about completeness relation. If you have any doubt, you can just ask me. Then I will go for my final thing about the eigenvalue and eigenvectors. Okay, so you can just use this thing very frequently. A number of time we will try to use. So let's finally we will go for eigenvalue and eigenvectors. So let's finally we will go for eigenvalue and eigenvector. Obviously, this eigenvalue eigenvector is used in n number of places, but we will just talk about only about the quantum mechanics level of this concept. Suppose I get a operator, and this operator is going to operate on some kit. What I will get? I will get exactly same kit in a proportional way. If I have any operator, it is going to operate on some kit, and I will get the same proportional kit. Because if operator will operate on any kit, it is not necessary, sorry, it will not necessary that it will get you same kit. Then phi is identified as eigenvector of operator A. Means you have any operator, any vector phi, you are just operating A on it, you will get exactly same vector. Not exactly same, it may be dimension wise, it may be different, but it should be exactly same vector. Now, so obviously there is some proportionality constant. So you can have A phi is equal to lambda phi. And here the phi, the lambda is identified as eigenvalue. And eigenvalue is just a number. Don't worry. Eigenvalue is just a number. And phi is identified as eigenvectors. And obviously this phi must be, obviously it should be non-trivial solution. So it should be not zero vector. So zero vector is a trivial solution. So we will just go for non-trivial one. So if we are going to solve it, so this will be A minus lambda I phi must be equal to 0. Phi should not be 0. So I can have A minus lambda I, determinant of this is identified as characteristic equation or secular equation. I prefer to write a secular equation. And the solution of this determinant will get you the eigenvalue. The solution of secular equation will give eigenvalue. Secular equation will give the solution of secular equation that will give you eigenvalue. And yes, eigenvalues, you can have n number of eigenvalues, depends on what are the dimension of matrix. So if A is n dimensional, then you can have n number of eigenvalues. So for n cross n matrix, we have n number of eigenvalue. So there are, if eigenvalues are repeated, so you have to always keep in mind, if eigenvalues are repeated, then they are degenerate eigenvalue, and if they are non-repeated, known as non-degenerate eigenvalue. Now, the most important thing is that in quantum mechanics, you have to find the eigenvectors corresponding to eigenvalue who should follow the completeness relation. This is the challenging thing. So I am just giving you the final line, but this line is the very interesting and very important. And in quantum mechanics, one should find eigenvectors corresponds to eigenvalues such that they will follow completeness relation, or you can write, one should find eigenvector phi n. I have written phi n such that they will follow phi n summation over n must be equal to I. So it's a very important. It is the actually we need it, and how we can do it. It's a very important thing, and this is the most challenging thing to getting all this thing. So this is basically known as completeness relation. So in today's class, the most important thing is all about the completeness relation, whatever we have learned. So I think my session time is over. So tomorrow's class, I will start with a little bit doubt, and then we will go for one beautiful problem of eigenvalue and eigenvector. We will try to discuss what is the actual problem into quantum mechanics, and then we will go for some problems on this particular. Then we will go for commutators, and obviously commutators are also operators. So we will try to go for some problems. So tomorrow class is the problem based on all these things. Okay. So I hope you enjoy these classes. Okay. So I'm just leaving. Tomorrow I will take your
Thank you,
doubts.
sir.
Okay.
Thank you, sir.
Okay. Thank you.
Thank you, sir.